Hello, Algebra 1 class. This is Mrs. Levenseller here. And today we're going to start with the first topic in Unit 1. We're going to talk about classifying real numbers. So the first learning target that we're covering is I can classify numbers in the real number system. Well, we are looking at this diagram below. The real number system, this is sort of a visual representation of that. So the real number system, those are all the numbers, the set of all the numbers that you have been used to seeing the whole time you've grown up, all right? And when we say a set, it's just really a collection of the numbers. So the real numbers, that's the umbrella term for all of the numbers that we're going to talk about. And under that umbrella falls rational numbers and irrational numbers. So it splits itself into two different sides here, rational and irrational. If you notice, underneath the irrational numbers, there aren't a bunch of other terms or bubbles or anything else, right? There's nothing here. That's because irrational numbers are their own category, okay? But rational numbers, however, those can be broken down further into integers, whole numbers, and natural numbers. The natural numbers are nested inside of the whole numbers, and the whole numbers are nested inside of the integers, and all of those things would be classified as rational numbers. So it's one of those things where a natural number is a rational number, but we can't necessarily always say that a rational number is a natural number, right? It doesn't work both ways. The smaller bubbles here, those would be part of the larger classifications, but the larger classifications can't always be considered the smaller classifications. So let's talk about some of these number sets and what they actually mean. One of the things that it might be interesting to notice is that when we talk a lot about math, there are a lot of things that come in pairs and they come in opposite pairs, right? So positive versus negative, that's an example of an opposite pair. So in this case, that's what we call a dichotomy. When you have two things that are opposing, they're opposites, it creates a dichotomy. Multiply and divide. They both are operations, but they are opposites, okay? When we look at this number set up here, we had rational numbers. What was the opposite of rational? It was irrational. That prefix IR is negating rational. So irrational is the opposite of rational. And then I want us to think about this here for a second. We have this whole number system that's called real numbers. What's the opposite of a real number? Right? Some of the answers you might be coming up with in your head are fake numbers, non-real numbers, and the answer is almost as logical as that. What we call the set of the set that's opposite real numbers, we call those imaginary numbers, or actually complex numbers is the larger umbrella they fall under, but we'll stick with imaginary numbers for right now. So real, the opposite of those, would be imaginary, okay? We are mostly going to stick with the real number system here, but I do want you to think about how large math is, okay? What you've learned up until now, and you're probably, 14? You've only learned about the real number system. There's a whole nother system of numbers that are imaginary or complex, okay? And so if you get into higher math, you can take full classes on these different sets of numbers and how they work and all of that. You'll see some of them when you get into Algebra 2 and Pre-Calc, but for the most part in Algebra 1, we're going to stick with real numbers. I do want you to just know, though, that there's a whole nother set out there that we can study. And if any of you are interested in that, I can certainly give you some more info on that. So now that we've sort of figured this out here, let's define what these different number sets are. Okay, so the real numbers are all of the rationals and irrationals put together, okay? So all rational and irrational numbers, okay? And like we said, it's essentially every single number you've ever come to know, okay? Then they're split into two components, rational versus irrational. So the shorthand way to think of a rational number is any number that can be written as a fraction. If you want the technical definition, it's any number that can be written in the form a over b, where a and b are integers, so we have to get to what an integer is in a second, and b is not ever 0, okay? Why can't b be 0? Because if you have something divided by 0, that doesn't actually work, right? That's undefined. So we can use any other thing for b except for 0 that is an integer. And really, again, this is just a fancy way to say, hey, we can write it as a fraction, okay? So keep that in mind. Rational, I like to think of that word as it makes sense. You're a very rational person and orderly. Well, rational numbers are anything that can be tidied up and written like fractions, okay? So the opposite of that is going to be your irrational numbers, which means they get a little crazy, right? So irrational numbers are any numbers that can't be expressed as fractions. And so think about what kind of numbers that would be. Oops. All right, what kind of numbers can we not write as fractions? Well, if you think about the number pi, it's maybe the most famous one, 3.14159265355 ... that number can go on for a while, right? And the tricky thing about pi is that the digits never repeat, okay? So if you have a non-repeating decimal, there's no way we can write that as a fraction. That's why we created an entire symbol to represent it, because this number is out of control. So any number that can't be written as a fraction is usually a value like a square root maybe, pi, something that has a decimal that doesn't terminate and doesn't repeat, okay? Now we get into some of the other types of numbers that are falling under the rational numbers. So rational numbers, part of those are the integers. When I like to think about your integers, I think of your number line numbers, okay? So anything that's on a number line. So it's the whole numbers and their opposites. So whole numbers, which we'll get to in a sec, are like 0, 1, 2, 3, 4. And the opposites, -1, -2, -3, -4, etc. So anything that generally shows up on your number line is considered an integer. Positives, negatives, and 0. Positives, negatives, and 0. Whole numbers, those are also under the classification of rational numbers. Whole numbers are part of the integers, right? So whole numbers are the integers without the negatives, okay? So 0 and all positive integers. All right, so whole numbers include 0. That's a really important point. So you would list them out as 0, 1, 2, 3, 4, etc. Okay. And then natural numbers are an even smaller set, and they're chunked underneath whole numbers, but they are also considered rational numbers, right? Natural numbers are whole numbers are integers, so natural numbers are integers, right? That sort of thought process that you'll expand on in geometry a little bit, that's really helpful here to think about what sets belong to which other sets. So natural numbers, the only difference between natural numbers and whole numbers are that natural numbers, we refer to them like the counting numbers. So it's the whole numbers without 0. And it seems like a really small difference, right? You're like, why did they make a whole different set of numbers if it's just one value we're leaving out? And the reason is that when you get into higher math, you're usually trying to prove that certain concepts are true. And sometimes, because 0 is such a funky number and it's not positive nor is it negative, it's really hard to prove some things are true with 0, but you might be able to prove that they're true with the rest of the positive numbers, right? So when we are trying to prove something for a certain set, the difference between having 0 and not having 0 is important. And one little thing I am going to tell you about the real number set is that we do have a symbol for it, and it's a capital R with an extra line here. So that means real numbers. That's how you shorthand that. So just be aware as we get further in the year, this might come up more often. It's also a quick abbreviation for you. The other sets have different symbols, but we don't use them as often. The real number one comes up quite a bit. Okay? So let's try and classify. So I have made this chart here. And what I would like you to do after we do the first one is to pause the video and see if you can fill in this chart, recreate it in your notebook, and fill in this chart for yourself, and then turn the video back on, and we'll go through each one together, okay? So let's do the first one together. The first one is the number 0. Well, we know 0 is real, all right? We know it is rational because I can write it like a fraction, right? 0 over 0. If it's rational, then it can't be irrational. If it's an, would it be an integer? So is it a number on our number line? Yep. Maybe that's a confusing way to mark it with an X, but that means that it can be that classification. So it is an integer because it's on our number line. Is it a whole number? 0 is part of the whole numbers, but it's not a natural number, right? So that I can't fill in. 5 is a real number. 5 is rational. I can write it as a fraction, 5 over 1, which means it's not irrational. Is 5 an integer? Yep, shows up on my number line. Is 5 a whole number? Yep. It's 0 and higher are the whole numbers, and it's positive 5, so that works. And it's a natural number. It's one of my counting numbers, okay? So pause the video here. I would like you to go through the rest of these values. I will scroll up, or just, there we go, zoom in, and see if you can classify each one of these values, and then tune back in a second, and we will go over them and see how well you did. Okay, so hopefully you had a chance to think about that. So now let's take a look at -2. -2 is real. It is rational. I can write it as a fraction. It is not irrational if it's rational. It is an integer because it shows up on my number line, but it's not a whole number, and if it's not a whole number, then it can't be a natural number, right? The natural numbers are part of the whole numbers, so that won't work. And there are no negatives in either of those. Okay, maybe that's a good reminder for you. No negatives. Pi. Pi is a real number. Pi is not rational, though. It is irrational. And remember, if it's irrational, it can't be any of these other things, because all of those three things, integer, whole, and natural, fall under rational numbers. So if it's irrational, that's all we have to check. Let's get a different color here. The square root of 36. Well, we talked about simplifying our radicals before. Think about what the square root of 36 is actually equal to. Well, we know that 36 is a perfect square, so the square root of 36 is 6. So yes, 6 is a real number. It is rational because I can write it as a fraction. If it's rational, it's not irrational. It's an integer. It's on the number line. It's a whole number, and it's a natural number, okay? So always think of the simplified version of your radical if you can, and use that to help you identify what it would be. So next, we have absolute value of -3. Well, what is absolute value of -3? It is just positive 3. -3 is 3 spaces away from 0. Well, positive 3 is real, rational, an integer, a whole number, and a natural number. Square root of 5. Well, Square root of 5 is not a perfect square, right? So I know that it's between the square root of 4, which is 2, and the next one up would be the square root of 9, or 3. So it's somewhere between 2 and 3. I am going to assume that we're going to get a pretty crazy decimal if I can't simplify that radical at all, if I can't think about what would come out of it. And you could double check this with the radical ones. You could double check that on your calculator to see what the decimal looks like. But we can pretty much surmise that it's not going to be a nice terminating decimal. So then that tells me, yes, square root of 5 is real, but it is irrational, okay? And that means it can't be rational or any of the other classifications. Now let's do 3 over 2. Let's get a different color. So 3 over 2, well, it's already written as a fraction, so that tells me it's rational. And if it's rational, it must be real. And we know that's 1.5, right? So keep that in mind. It's a terminating decimal. If it's rational, it can't be irrational. Integers, whole numbers, and natural numbers, though, none of those have any decimals or fractions. So it cannot be any of those last 3. All right. Let's see here. Next, we have 0.3 repeating. And I've just listed 2 different ways to write that, okay? So with the ... after, or with the bar across it. Well, 0.3 repeating, it's a real number for sure. Is it rational? So it's a repeating decimal, but do you guys know what 0.3 repeating is actually equivalent to? It's equivalent to 1/3, all right? So actually any decimal that repeats the same number over and over and over again, those can all be turned into fractions, and usually it's a fraction with the denominator of 9, so I could rewrite 0.3 repeating as 3/9, but that reduces to 1/3, okay? If I had 0.5 repeating, that would reduce or become 5/9, and that can't be reduced. So any decimal that has a repeating value, same thing over and over and over, that is going to be a rational number. Oops. And it is a fraction, though, so it's not an integer, nor is it whole nor natural, okay? Same thing here, 4.16934, those are decimal values that do not repeat. So I know it's real, but it is irrational, and if it's irrational, it can't be any of these others. It also can't be those because it's decimal, and it can't be rational. Negative square root of 81. Well, the negative value is on the outside of the square root, so that's okay. So the square root of 81, 81 is a perfect square, that gives me 9. So this is really -9, okay? So now think about its classifications. It's real, it's rational, which means it's not irrational. It's an integer, but it's not a whole number or a natural number because it's not positive, all right? And then 0.02, well, tens, hundredths place, this is the same as 2 100ths, okay? So it's real and it's rational because I just wrote it as a fraction. It's a terminating decimal, which means it's not irrational, but 0.02 is not something that would normally show up on your number line. So it's not an integer, and then it can't be whole or natural, okay? So one quick question here. What about the square root of -81? Right? So we said the negative square root of 81 is equal to -9, which is a perfectly real and rational number. But if you put this square root of -81 into your calculator, let's go try it here. So 81, I'm going to make it negative. And then I want to take the square root. It says error, okay? So when you see something giving you error, that should make you think, all right? Maybe that I'm not getting a real number when I do that. This is because when we talk about square roots, like the square root of 81, it's equal to 9 because two numbers, 9 times 9, they are exactly the same and they multiply to give me 81, right? But there are no two numbers that are exactly the same that multiply to give me negative 81. I would have to multiply 9 times negative 9. Those numbers are close, but they're not the same value, right? So because you can't have two numbers that are exactly the same multiplying to give you negative 81, this is where we can't take the square root as usual. When we do take the square root, we get an imaginary number, okay? And we represent that with the symbol I. So if you were actually taking the square root of negative 81, it would be equivalent to 9I. And whenever you see that symbol, that means you have an imaginary number, okay? For our purposes, I just want you to know that you can't take the square root of a negative and get a real answer. So anytime you see that, you have to just know that you're getting an imaginary answer, and when you get into higher math, you will actually do something with that, okay? But that's part of the imaginary